Start of question 7. In a car crash, a person, again, the hard part is imagining and viewing this problem in a way where it becomes a simple conservation of momentum problem. Let's try that technique that worked well in the other, for me anyway, your mileage may vary, of just reading the question and drawing what we read. In a car crash, okay, there's a terrible car crash here. A person can be injured by her seatbelt if the force that the belt exerts on her is greater than 16,000 newtons. Determine the minimum safe stopping time for a 64-kilogram woman driving at 25 meters per second. So, I'm not trying to solve anything. I just want to get it in the drawing, just to visualize what's going on here. Determine the minimum, so let's go back. Let's go reread. Can we add anything else? In a car crash, a person injured by her seatbelt, if the force is greater than 16,000, 1, 2, 3, count my zeros, minimum safe stopping time. Minimum safe, okay, look, there's a time interval in here somewhere. Okay, stopping time. So time interval. Interval is between what and what?
Time 1 and time 2.
Yeah, okay, an interval is between two time instants. What's going on at this time? What's going on at this time? Okay, let's see if we can find two instants in time when we know a lot about what's going on in these objects. Notice I haven't made any system choices yet, but let's see what happens. Let's walk a little ways down the path and see if things look more familiar. If this were time 1, what would I know? The car is going at a known velocity, or I don't have a lot of information about the car. I don't know the mass of the car. But what we want is, this seems to be concerned more with the woman. That's the mass of the woman. That's the velocity of the woman. So if this were T1, I would know a certain amount about this woman. I would know her velocity and her mass. And if I know that, I know her initial momentum, right? So let's skip ahead to another step of the problem-solving strategy. So if there were a bar for initial momentum of the woman, I would totally know what that was. Okay. So that's T1 took care of. T2. Is there another moment when I know a lot?
When the car stopped.
Student in the room, good old period 5, says, yeah, I know a lot about when the car is stopped. Or, when the woman is stopped. Her velocity is 0, which means her momentum is 0. So just for fun, where could that get us if we have something like this? What if what I can see from looking at this is, if we chose just the woman for our system, we would have all but one bar in our chart, right? So if we made that choice, we would know that initial plus change equals 0. So that means we would know what this change is. This delta P would be a known quantity. Does delta P appear anywhere that might help us get to this time interval? What's happening? Let's go back to imagination. What's happening in the world over this time interval? Over this time interval between...
Just do, can't you just do the velocity of the car? Or the velocity of the woman times the velocity, the mass of the woman? You know that's going to be opposite of the PWI.
Hey, that's great. Okay, that's the suggestion was let's calculate the initial momentum of the woman. We can totally do that. That's her mass times her velocity. 64 kilograms times 25. Oops, we've got a direction quantity in here. Let's go back and check our directions. So let's call this positive. That means here's a velocity. That's got to be positive. Any other velocities? So it's positive here. And that gives us a total momentum, initial momentum for the woman of 1,600 kilogram meters per second. So the size of this bar is 1,600. And like I said, that means this must be negative 1,600. So we've been pretty much just trying stuff in any order. So with luck, we should be getting a little close to C to recognize that when that we have an application of this principle. If something from outside the system is exerting a force on a system object, okay, this is the total force exerted by objects not in the system, and it exerts that force for some period of time, we can calculate the delta P, or the impulse, the change in momentum of the system. Since we know delta P from our chart, is there an object external to the system that's exerting force on a system object? I tell you what, did we officially define our system? Well, the woman is the only thing in the bar chart. What?
What about the seatbelt?
The seatbelt is definitely exerting a force on the woman. You know what happens to me? You know what confuses the heck out of me? This idea of, what does it say? Minimum safe stopping time? Maximum safe force? That makes my head hurt. What if I just say that the force of the seatbelt on the woman is 16,000 newtons and see what happens? Okay? Because I know that more than 16,000 would be bad. So 16,000 is not bad. Let's see what happens.